the low frequency voltage gain for the amplifier shown. And we have this following amplifier right here. We can use the notes linked below the like button in the description to find out what kind of amplifier this is. So using these notes on page 143, we have single transistor MOS amplifiers. And it has to look like one of these. Well, we've previously gone over this and we looked at one that's reverse and it was kind of tricky, but we found out which one it is. This one here we have our VDD, our RD, and then our M1, Vout, RS. So if we look at both of the right and left for most ones, these are the same, and then same thing with our RG and VI. What's different is our R not, right? What it's paired with. And we can see that with this one, the arrow is pointing downwards and out, down and out, where the previous one was just pointing inwards. And our R naught is the same with our V naught. So that means it's going to be a common drain amplifier. So common drain amplifier is also called a CD. So now that we know this, we can find the voltage gain for it, because the question is asking us for the low frequency voltage gain. And for voltage gain, we can scroll down to this specific section with our common drain, and it's going to be this AV equation right here. So we can take this and we are going to paste it inside of here so that we can use it. Now that we have this equation, we can look at it and we can plug in our values. Well, there's something that we cannot plug in, and that is this GM right here. We don't know what our GM is, nor do we know what our GMB or our GDS is. So let's look at our GM first. With our GM, we are going to set it equal to, and if we look at the notes on page 92, we have this GM equation. We can just do a Control or Command F and find it, and we're going to use this one right here because it corresponds to the values that we have. So this is equal to the square root of 2 times our K prime times our W over L, and this is being multiplied by R I D. And so now we can plug in our values. After we plug in our values, we're going to get that our GM is equal to approximately 2.0894, and this is measured in milliamps per volt. So this is going to be our answer for GM. Now, what about our GMB and our GDS? Well, they're two different things, and for our GMB, it's actually going to be a little bit small, but it's going to be equal to 0. I'll make this bigger in a second, and it's because of the neglection of body effect. Now, our GDS is similar, except we are going to set it equal to 0 because we neglect the channel length modulation. And that last part, it actually tells us in the initial question, it tells us to neglect the effects of channel length modulation. So that is going to be how we would solve for this. Both of these are going to be 0 out. So we'll take these and not include them when we plug in our values. Our RS and our RS is given, so these two values are the same, 0.7 kilo ohms. We plug in all of our values, and once we are done with this, we are going to get that our AV is equal to approximately 0.594. Note that AV is always positive, but less than 1 as well. Now, if we wanted to find our R, we would look at something like this. So we have our RI equal to our RIG, and this is for the open circuit, looking into the gate at the low frequency. And this is also in the notes, not in this section, but in this section right here. RI is equal to RIG, and that's equal to infinity. And we can find our RI and R naught with the equations down here. And this is just demonstrating it. RS is parallel to 1 over GM, so that is the equivalent of this large equation that we have here, just simplifying it down. And that's how you would go about solving this problem in this little extra part right here.